Okay, so hi, my name is Daniel. Thanks for having me here. We're going to talk about how we can share our thoughts with the compiler and why it's going to be useful for us. This is going to be a beginner-friendly talk, I hope. So before we actually begin, I'll start with a quick intro to get us in the appropriate mood. So here we have two branches. So in one we have a sum of a string, and another we have a none. And yet again, you hit enter, and you get a reasonable type. So the compiler managed to infer the right type for us. So in this case, an option of string. And this is quite nice. So at this point, you're thinking maybe the compiler gets you. It's kind of it's a good feeling. You feel like one with the machine, like you know what the compiler is thinking. It knows what you're thinking. And it's a nice feeling. Sadly, it doesn't last for that long. And so we continue. So now we're using our favorite JSON library to write some numbers. And in this case, we're just writing a plain number, and it works as you might expect it to. And then do something more sophisticated. So we're taking an option of a number. And again, an option of a number is quite similar to a number, so it works again just as well. And then you do something more advanced. So we're trying to write a trie of a number. And you're thinking a trie of a number is kind of like a number, like an option is kind of like a number. But then the compiler screams at you something incomprehensible about something, and you kind of can't figure it out, and you probably give up at this point and just move along with your options, not tries. And then further down the line, you're writing something more sophisticated. So now it's you're writing your app now. You're trying to fetch some data about the post. And then sometime later, during the night probably, in your production system, you get some exception. And after debugging it for a long time, trying to figure out what it is, you get that the signature of this function is actually wrong. We switched the feed ID and the post ID, and so we got an exception. And you're kind of disappointed because it's a dumb mistake to make. Why didn't anyone help us catch it before actually writing this code? And so as you go along, the image of the compiler kind of changes gradually into this sort of kind of a monster that tries to haunt you with incomprehensible errors. And it's kind of annoying on the one hand, but on the other hand, it's kind of dumb because it can't catch like obvious errors like the one on the previous slide. And my claim for this talk is that this doesn't have to be this way. Actually, we can do much better and actually leverage the compiler for our benefit. And the key point of this whole talk is communication. We need to try and communicate with the compiler as much as possible, and if we communicate ideas or knowledge about the code to the compiler will help us back and be more useful in our development process. And for the purposes of communication, we're going to use three ways of means of communication. And so we're going to look at types, implicits, and macros, each one providing us with some way of communicating knowledge to the compiler and getting some feedback back. And once the compiler actually understands our intents, it can help us out writing our code and guide us or catch mistakes and whatnot. And so we begin with types. So Scala's type system is quite famous or infamous for being advanced. As we saw in the previous talk, we can do quite complicated stuff with it. But we're going to use it to leverage the type system for communication with the compiler. And so for the purposes of this talk, types are going to be viewed as compiler-verified facts. So it's a fact that the compiler can keep track of and verify its consistent usage. So if we declare that something is an int, the compiler is going to make sure that we use it consistently as an int for us, and we can't make mistakes regarding that parameter. And as a corollary of this fact, the more types we use in our application, the more consistency checks we get back from the compiler. And the more precise the types that we use, the actual checks that the compiler does are more useful. And since Scala's type system is advanced, we can encode sophisticated knowledge into our types and let the compiler keep track of them for us. So let's start with a simple and very useful technique. So we go back to our fetch post function. So the problem with the signature, we are using types, so we have integers, but those types are not descriptive. So nothing tells the compiler that the app ID and the post ID are distinct concepts. So it doesn't know that this int is somehow different from another int. And so we can mix them up, and the compiler won't do anything about it. And we can somehow make it less painful if we use named arguments. So the order of the application doesn't matter because we name each number with its own name. And this is better than the previous attempt, but still it's local knowledge. We're not encoding anything that the compiler can actually keep track of globally. So if you want to ask where are all the places where we use integers as application IDs, the compiler won't know and won't be able to actually tell us that. And so what we're going to do is we're going to use wrappers, typed wrappers. And so for each concept in our system, for each thing that we're using, we're going to create a small case class that wraps them. So we have app ID, post ID, and feed ID. So each one wraps an integer value. And so since we're introducing a case class or a new type for this purpose, the compiler can now keep track of them separately and verify the consistent usage of each one of them distinctly. And so, and since Scala syntax for this is quite compact, it's actually that doesn't really cost us much of mental overhead to actually sprinkle those around and just wrap every concept we have in our system with a dedicated type. And now we can rewrite our signature from before. So now it's much, much more descriptive. So just by reading the signature, we can actually verify that it does the right thing. But what's more important here is that the compiler can read this thing as well. So now actually knows that the app ID here and the post ID here are two completely distinct concepts. And it can keep track that we're using them as appropriate. And so if we try to do the same vocation we did before with the arguments flipped, we're going to get a compilation error. Telling us that we did something wrong. So by using our types to communicate with the compiler, we managed to get some feedback from it back. So in this case, it's actually quite meaningful and readable, like some type errors. So we can actually see quite easily that we mixed up two things together. So we managed to leverage communication for our own benefit. And so we can these small type wrappers are actually one of the most useful techniques I have in my code, I think, because just spreading them around makes lots of things much more easier. And so, for example, we can now search by type. If I want to ask the application, ask the compiler, where do you use application IDs in our code, we can just search for the application ID type, and it will find all the usages for us. Which is something which is not possible with integers because they're all around and we can just search for specific ones. We can also refactor more easily. So if you want to change the application ID from int to long or something, it's quite simple. We just refactor we just change the type and see the compilation errors and track them down and fix them. We also can customize the usages of our special wrappers. So we can do smart constructors where we can verify some invariants about our types. So suppose application ID has to be a positive number, we can verify it at construction time, and the compiler will keep track of our usage of this function. It won't let us instantiate new application IDs with invalid values. And we also can customize serialization. For example, if you want to, say, encode some IDs, we can have special serializers for our special types, which is not that convenient to use with just integers, but with specialized types, we can, the compiler will keep track of this for us. And so all of these are side benefits of using more precise types in our code, and I find it very, very useful. So I want to make a small interlude for a small rant. So suppose you found your dream job, and it's all-day Scala. You think, OK, I'll never see scary code in other languages. Everything is going to be great. And it's kind of a reasonable expectation. But then you're writing your web app and doing some, and you have something like this. So it's like a template for something. And in this case, we have here like 3 languages. We have HTML, we have JavaScript, and also the weird little language for URL syntax, which is also kind of a small language in itself. And so we're mixing all this together. And not only that, but actually we're doing interpolation into our code. And so every place where we interpolate some variable into, where are they? So interpolate a variable into our code, we're risking a code injection, for example. And there's no one to actually help us. Like, no one is going to hold our hand and make sure that we're using the right variables in the right places. And it's difficult. It's hard and it's quite annoying. And now, since we're here, we're into communicating with the compiler, let's try to mitigate this issue with more information for the compiler. So we can start with typed wrappers. So In this case, we have now 3 wrappers, one for HTML, one for JavaScript, one for URL. So the compiler can keep track that we're not actually using the wrong kind of string in the wrong kind of place. But as I mentioned before, we're doing interpolation. So since lots of the things that we might interpolate will come from user input, this might be unsafe. And we would like the compiler to actually keep track of the safety properties of the strings that we're using. And so we might introduce something like this. So we have a tainted HTML code, which means that we've read it from user input, but we didn't sanitize it yet. And so it's not safe to interpolate anywhere. Now, since we have the tainted variants, we should have the safe ones, which indicate that this value was already sanitized in the appropriate language. So we have safe HTML code, safe JavaScript code, and safe URL code. But then maybe we have some more requirements. Suppose we have now sensitive user data, and we don't want to actually interpolate it before we anonymize it in some way. So we might have more wrappers. And so now we have sensitive variants of all our previous cases, but also we have the anonymized ones. And obviously, this is getting out of hand. Something is kind of wrong here. And just the names of these case classes are already a code smell, and we're not trying to use them. Just defining them is kind of horrible. And so the problem here is that we're using these simple types to encode multiple facts about our actual values. So in this case, when we're saying something like sensitive, tainted HTML code, we're encoding 3 different facts into a single type. But from the compiler standpoint, it's a single concept. Each case class, each type is a distinct concept that the compiler can keep track of as one unit. It doesn't know anything about the separate 3 concepts of sensitivity, safety, and languages. And so we hadn't communicated enough with the compiler, so we were not getting something useful from it back. So we'll try another technique to make it somehow more tractable for us. So I'm going to use phantom types, and I'll explain shortly what this means. So we start with encoding the concepts that we have in our code. So we have the concept of language. So we have a trait for languages, and we have 3 cases for this trait. So notice that this is a still trait, and all the subtypes are traits as well. So we can't have any values of this type language. Since it's a type without values, we call it a phantom type, and it's here solely to communicate with the compiler. It doesn't have any runtime usage at all. It's just so that the compiler knows about a new concept called language in our code. And we can do the same thing with the concept of safety. So we have type safety and 2 cases, tainted and safe. Again, a phantom type, so we don't have any values. And we can do the same thing with anonymization, but I'll save the slide space and move along. And so now that we have those 2 concepts in our system as the separate distinct concepts, we can use them again, using again another wrapper, but this time we're going to use something more sophisticated. So now we have a wrapper around the string, but now it has 2 type parameters, one for language, one for safety. So we have 2 distinct concepts around each wrapper, and we can use them separately. Now the compiler can also keep track of them separately as well. And so if you want, we might have a function that reads HTML input, so it creates an input code of HTML and it's tainted. So the compiler knows that it's tainted and won't let us use it in an unsafe way. We might have a sanitize function that takes tainted code and converts it into safe code. And ideally, in a real system, this will be the only way to obtain a safe piece of HTML code so that the compiler can keep track that we're never using tainted code, we're never creating safe code by mistake. And then the last part would be to actually interpolate this code. So this function expects only safe code, and only then it produces a code value, the final code value with everything interpolated. And so the compiler can actually make sure that we're doing the right thing since the types are descriptive enough. And suppose we do something wrong. So we're reading a string, HTML string, and now it's a tainted string, and try to interpolate it directly as it is, and the compiler will tell us that you're wrong. You're doing something that's forbidden. In this case, again, it's quite readable. You can easily fix this and figure out what went wrong. Also, since the concepts of language and safety are not distinct, we can actually operate on one without touching the other. So with the multiple wrappers we had before, it would be quite tedious to actually operate, say, only on the language, but not on safety or something, since we'll have to duplicate code against each combination of case classes. And so we can have a function called anonymize that doesn't care about safety, so safety is a parameter, and it takes some HTML code with whatever safety and produces an HTML code code with the same safety as before, so it doesn't care about it. And if we try to do something wrong, so for example, take JavaScript code and anonymize it with the HTML function, again, we have a type error, and it works as you might expect it to. So again, by communicating various facts to the compiler, we obtain useful assistance in return, at least in my opinion. And so, as we saw in the previous talk, but generally, Scala's type system, again, is quite advanced. So there are various concepts that we can encode this way. So each kind of type we have in the Scala type system can help us encode a new sort of invariant into our code, a new family of facts that we can ask the compiler to track for us. And hopefully, the two examples in this part will give you motivation to explore further variants of Scala's type systems, and hopefully they'll be useful for you as well. So this concludes the types part. So, implicits have a bad name because, probably rightfully so, because it's easy to make a mess with implicits. So, for example, here's something that you should not be doing when you're writing your code. So, after taking the trouble of actually defining type wrappers for everything that for every concept in our system, in the previous part, we might do something like this. So here we have implicit conversions that take numbers and convert them into IDs. And so now the compiler is getting confused. So we told the compiler about the various concepts, but now we're telling that we can mix them up with integers freely. And so again, we can have the same bug as before. So we have 3 numbers, and the compiler just converted them automatically using the implicit conversions into our function. So again, we have the same bug. So this is something you should be avoiding, and try not to confuse the compiler and yourselves along the way. So what I actually want to talk about is about useful usage of implicits, and not something that just makes a mess. So for our purposes, so implicit every implicit is a piece of knowledge that the compiler can operate on, meaning that it takes some knowledge at compile time and can use this knowledge to derive new knowledge for us. And also, unlike types which are just types, implicits provide a connection between types and values. So when we declare some value to be implicit, its type is connected to that value. So the compiler can produce values just by looking at some types. And we'll see how this is useful further down the line. So what would be a good usage of implicits? So here, sort of the terminology I'll be using. So we have facts. So when we're saying that we have an implicit writer of strings, the writer is a JSON writer that can write strings. So we're saying that if I want the writer for string, this is the one that the compiler can actually provide for you, because it knows about it at compile time that this is the one that it can use. So guided by the type writer of string, we can produce the appropriate value. Next, we have rules. So a rule is something that the compiler can actually operate on. So if you read the signature, it reads like this. Suppose you know, for some A, suppose you know how to write an A as a JSON. I'm going to teach you how to write a list of A. So the compiler can, since this is marked implicit, the compiler can invoke this rule at compile time to actually generate new facts about things. So if I know how to write a string, I'll know how to write a list of string using this rule and this fact together. And to actually use this for our code, we have a derivation request, where we actually, when we mark an argument as implicit, we're actually asking the compiler to produce a value for us. And the compiler will use all the rules and facts that it knows to combine them all together and produce a value for us. So for example, if you do something like this, writing a list of strings, it will produce the correct writer for us. So it managed to combine the known rules and facts into a new value for us. I actually think that the name implicit is kind of the thing that scares people off, because when you think implicit, you think about some background magic happening without your out of control somewhere. I think if we kind of change the name and use something more descriptive, something that actually tells us that we're communicating with the compiler and not just doing some magic in the background, maybe it'll be less scary, I hope. And so in my made-up language that allows using dashes in keywords, we'll have 3 things. We'll have compile time facts, like a fact about writer of string. We'll have compile time rules, which are rules from some value into another value. And we have derivation request, where we actually get a compiler-provided value. And so with this terminology, it becomes more apparent that what we're doing, we're actually communicating with the compiler. We're teaching it about new rules and facts, and it can combine them in useful ways and provide values for us. And so all this is maybe a bit abstract, so let's actually look at some code that does something. So an implementation of a writer of string does the obvious thing. It takes a string and wraps it in a JSON string constructor. And so here we are telling the compiler, this is the writer of string. Every time I ask you for a writer of string, you can use this value and do whatever you want with it. Next, we have an example of a rule. So if we know how to write an A, we can write a list of A. How we do it? We just take the list of A, map over it. Every A value in this list we're writing with the writer that was already provided for us. And then we wrap the whole thing in a JSON array. And so the compiler can actually use this rule whenever we ask it to write a list of something. Next, we'll have another similar rule for options. So suppose you know how to write an A, you can also write an option of A. So it's quite simple. You either write the value directly or write a null if it's missing, a JSON null in this case. And so we can now actually ask the compiler to do some work for us. So suppose we have a list of options of strings. If we try to write those values, the compiler will happily do it. And do it for us despite not actually telling it how to write lists of options of string directly. And how does it do it? It actually derives the value for us. So when we're writing this thing, in the background, the compiler takes the two rules and the fact from the previous slide and combines them into a single value. So in this case, what it did, it invoked the list writer rule, the option writer, and the string writer fact, and derived this value for us and placed it in the implicit invocation. So this is code that we didn't have to write. So we taught the compiler something, and it gave us back some useful knowledge, or useful value in this case, to use in our code. But suppose we miss something. Suppose we're trying now to write a list of try string. So we didn't actually teach the compiler how to write tries of things. And so obviously the compiler can't actually derive things by magic. It has to know, has to have some rules to actually do this. And so in this case, the compiler gives us an compilation error telling us, OK, you're trying to write a list of try of string, but I have no idea how to write it. And so it might be not obvious that it doesn't actually know how to write tries, but still, the compiler attempts to tell us that we're missing some piece of knowledge that we should have provided it previously. And if we try to sort of debug it, so if we try to derive a writer for a list of try of something, so we can invoke the list writer rule, but we don't have anything to provide the list writer rule with. So the compiler is getting stuck with not being able to do anything. So we can just step up just a little bit. So we can have more advanced rules where we take more knowledge and convert it to something more complicated. So suppose we know how to write an A and a B, we can also derive a rule that can write a tuple of A and a B, and the same goes for iders. And you can say define this value, and its type is so long that it doesn't actually fit on the slide, and don't do this, it's just for illustration purposes. But the thing is that we have this long type, and we have some rules that the compiler knows about, and we want to use those rules to actually write those values. And if we do this, if we try to write this complicated value, the compiler will happily do it for us. And in the background, it does all this. It invokes all of those rules. And imagine how tedious it would be to actually write this out yourself. And the compiler does it for us. We taught it the right facts and rules. It can do the rest for us. And using this type is probably not practical in any application, but having deeply nested types is actually something that we do have. And once you teach the compiler the appropriate facts and rules, you can actually count it to do the work for us. So hopefully this illustrates how implicits can be used to communicate with the compiler, how we can share various concepts with the compiler through implicits. And this example was sort of an example of type classes, and we have a talk later on about type classes. But there are other patterns of usage with implicits. So we can have type-driven dependency injection, and we can have other things. And also, to note, the shapeless library does very sophisticated stuff using implicits. It can encode some very advanced knowledge about various types using implicits, and hopefully this will give you the motivation to explore things like shapeless further on. So now we're ready for last part, macros. And macros are scary. People, rightfully so, are scared of them. But they do have their uses, and we'll try to see what they are. So what are macros? So macros are compile time functions that take code or abstract syntax tree and produce new code at compile time. And also, since it's a function, it's a regular Scala function that runs at compile time, and you can actually invoke any code from the macro invocation. So during the evaluation of the macro function, we can say talk to a database, which sounds kind of weird, but it's not unheard of. And they're still experimental, and all of this is just as dangerous as it sounds. It's sort of not unlike this situation where you the compiler is this truck and you're kind of trying to fix it midair with something new, and it might break, might not, but who knows? And you might ask, why would you use something like this? Why would you risk being crushed to death by a truck? So the answer would be, as a last resort, only one standard means of communication fails. So if types and implicits or other methods fail, macros might be the solution to this problem. And they should be considered only as a last resort, not as a first thing. And so various use cases for macros include implementing missing language features or to cut down on some boilerplate where writing out the code would be repetitive or error-prone. We can use macros to actually make it easier. But in a sense, macros are the ultimate way of communicating with the compiler, sort of go into the brain of the machine and just put knowledge inside its brain. And so it can be useful, and let's start with a simple example. So Scala has nice support for regular expressions, so we can write a regular expression and sort of pattern match on it, and it's kind of nice. But sadly, if we have mistaken our regular expression, so here I forgot to close the parentheses, what we get is a runtime error saying that, well, we missed something. And it's kind of sad that we can't have this at compile time, since the string literal is kind of quite easy to actually verify that it's correct, like at compilation time. But the Scala language doesn't support it, doesn't know about regular expressions at compile time, and you can't do anything about it with just types. Maybe with implicits, but probably would be quite scary. And so what we would like to do is to teach the compiler to handle implicit, to handle regular expressions at compile time. So we're going to write a macro that does exactly that. We're going to have compile time checked regular expressions. And I'm going to use simplified versions of macros. They're not quite robust. I'm not going to delve into the details of macro implementation because they're quite technical and not, I just want to illustrate the concept of using a macro. And so we start with some boilerplate. So we define the macro signature. So we're taking a string and produce a regex type. But instead of actually implementing this function, we use the macro keyword to say that we're going to implement it using a macro. And the implementation resides in the regex simple function. Next, we have more boilerplate. In this case, we're taking a context, which is the way the compiler, the way we can actually take some code writing tools from the compiler and use them during the invocation of the macro. And then we receive an expression of string. So expression of string is the code representation of the code that we're receiving at compile time during the invocation of the macro. And the result is going to be more code. So in this case, a code that type checks as a regular expression. And this import is crucial, but I'm not going to explain exactly what it does. And so first thing we want to do, we got some code that represents a string, but we actually want to work only on string literals. So we're going to pattern match on the tree of the code that we received. And so we're using a thing called quasi-quotes, this Q and string, which allows us to deconstruct code and write code with fairly simple syntax. So in this case, this pattern match is going to succeed only if S here, the literal tree that we're pattern matching on, is an actual string literal, nothing else. Otherwise, we're going to abort. In this case, it's aborting the compilation. So it's a compile time error to hit this branch. So if we pass this point, the string literal here is an actual literal string that we can inspect now at compile time. So we want to verify that it actually corresponds to an actual regular expression. So we're going to convert it into a regular expression. But since this might throw an exception, and it's going to be an exception thrown at compile time, I'm going to be careful. So we're wrapping with a try. And if this whole thing succeeded, so the string actually corresponds to an actual regular expression, so we can just ignore it. Otherwise, we're going to, again, abort compilation and produce a useful error message. So this is happening at compile time, not runtime. And it's going to stop the compilation process and not blow up at runtime. And last thing, the last part is actually produce the code that we're promising the compiler that we're going to give it a code that corresponds to a regular expression, and this does exactly this. We're taking the string literal, invoking the R method on it, and wrapping it all in a quasi-quote, which actually produces the code that corresponds to this string. And this completes the macro, and we can actually use it. If the regular expression is correct, it just works as you might expect it to. But if we provide it with an invalid regular expression, we get a compile time error. So quite useful one, telling us exactly what went wrong. And so that's exactly what we want to achieve. So we taught the compiler something new. We dug into its brain and sort of placed a new technique into its brain. And now it can actually apply this technique to our code. Now let's move on to something more complicated, another example of using macros. So up until now, we used macros just to, we used the writers only for simple types like strings, lists, and stuff like this, but we didn't actually do anything custom. So for example, suppose we have a case class with some fields, and we would like to have a writer for it. So we can write this, we can implement the writer ourselves. It's quite straightforward. So we're going over all of the fields of this case class, so name, ammo, and dangerous, convert them into strings, and then tuple them with a JSON write of the value of the actual field. And this code is quite tedious to write, especially if we have more fields, and nothing is going to keep this in sync with the actual implementation of the case class. And so it's a boilerplate, and it can be slightly dangerous if we forget something, and can be error-prone if we just write the string, misspell the string here or something. And so we would like to avoid writing this code, because it's quite mechanical. Just go over every single field and do some fixed action on this field. But sadly, the Scala language doesn't provide any way of manipulating case classes at compile time. And so this is, again, a use case for macros, where we can actually cut down the boilerplate by teaching the compiler how to do this for us. So we, again, have some boilerplate. So we start with the signature of the macro. So it takes an A type, the type for which we want to derive the actual writer. And this tells the compiler that it has to provide some knowledge about this type at compile time for us. So weak type tag is something that we can use to actually access knowledge about the type that we're trying to process. And now this TPA value is actually the value that the compiler provides us that holds knowledge about the type that we are processing now. Next, we're going to try to extract all the field names from this type. I'm not going to show the actual implementation of get fields. It's not that complicated, but slightly technical and hairy. But the concept is simple. We just go to the main constructor of the case class and take all the named arguments it has, and put them in a single list, a list of term names. And now that we have those term names, we are going to convert each term name into a piece of code. So we're going over the fields. We create a quasi-code. So this is actually code that's going to be written in the final implementation of the macro. And so we're turning the field representation into an actual string. And we tuple it with a JSON write of accessing this field with the value. So this is exactly the code that we were writing previously for the case class, but in a more generic way. And so now that we have the writing of the fields, we're going to interpolate it into an actual writer. So we're creating, again, a quasi-quote of a new writer with the right type. And we're going to implement its write method with an actual JSON object in which we're placing a list of those pieces of code. And this double dot syntax is actually interpolating this list as a list of arguments inside this code. And so this actually completes the implementation. So this will provide the right code when we try to invoke this macro. And so if we try to use it, so we're asking the compiler to make a writer for the terminator case class. It's going to do exactly that. And this code corresponds exactly to the code I showed a couple of slides back. And we can use it, and it works as you might expect it to. So this is boilerplate that we didn't have to write. We taught the compiler how to do it for us, and now it just does. So yet again, we managed to teach the compiler something new, and as always, it's quite beneficial. But as I said, macros are to be avoided if possible. Here, shapeless, again, figures as something that can replace macros in some use cases. So shapeless has some very clever macros that are implemented in the library, but it provides a very generic, some very generic interfaces to actually do stuff that macros do, but without us writing one. And so sometimes we can use shapeless to do things that only macros allow otherwise. Also, there's a newer project for metaprogramming in Scala called Scala Meta. It doesn't actually replace macros completely, but it does provide supposedly more convenient way of doing metaprogramming in some use cases. Also, we can approach code generators in some instances of problems with writing code. And the code generators are quite cumbersome to actually use, but sometimes are maybe easier than writing an actual macro. And as I mentioned before, macros are currently experimental in Scala, but the work is being done on creating non-experimental macros, and hopefully they'll maybe be simpler to use and overall nicer, but who knows. So, to sum up, the compiler is not your enemy. We should try to communicate with it, and the more we can communicate with it, the more helpful it can be for us. And we've seen three methods of communications. So types, which let us state facts to the compiler, and the compiler can keep track of. And implicits that let us teach the compiler about various rules and facts, and then the compiler can use those rules and facts to derive new knowledge for us. And macros as a last resort, which can teach the compiler completely new things that are not supported in the language. And so with all these tools in hand, we can share our thoughts with the compiler, and hopefully the compiler will share its knowledge with us, and the result should be something, a more productive process of writing code. And you can find the full code and the presentation at this link. And we're done. Questions? No questions. OK.